Is way more interesting than you might think, and it all starts with a very simple question.
So let me ask you something. Right now, as you're watching this, are you moving? You're probably sitting still, maybe in a chair, on your couch. So the obvious answer seems to be no, right? But in physics, the most obvious answer, well, it isn't always the whole story.
And that's because the real answer is, it depends. It completely depends on what you're comparing your motion to. And you know what? This single idea is one of the most fundamental concepts in all of physics, and it's exactly what we're going to unpack today. Which brings us right into our first section. We're going to solve this little puzzle. How in the world is it possible to be in motion and completely still at the exact same time? Let's use a classic example. Just picture this. You're sitting on a bus and it's driving down the road. Okay, now compared to the person sitting next to you or even the seat you're in, you are not moving at all, are you? You are at rest. But if someone is standing on the sidewalk and looks at you, they see you whizzing by. To them, you are definitely in motion. So you've got the same person at the same exact moment in two totally different states of motion. So how do we make sense of this? The key, the absolute secret, is this concept right here, a reference point. In physics, everything is described from a specific point of view. In our bus example, the bus was one reference point and the ground was another. The second you change the reference point, you change the entire description of motion. The bottom line is this: without a reference point, words like moving and still are completely meaningless. Okay, so now that we know motion is relative, we need to learn the language physicists use to describe it with precision. And it turns out there are two very different ways we measure the world around us. First up, we have scalars. A scalar is basically just a number. It's a magnitude. It just tells you how much of something there is. If you say you have a mass of 70 kilograms, or that 10 minutes have passed, or that you've traveled 5 kilometers, all of those are scalars. They have a size, but they have no direction attached. But what happens when direction really matters? Well, that's where vectors come in. A vector has both a magnitude and a direction. It tells you how much and which way. Think about it. Pushing a box with a certain amount of force isn't enough info. You gotta know which way you're pushing it. That's a vector. And that's it. That's the whole ball game. If you ever need to figure out if you're dealing with a scalar or a vector, just ask yourself one simple question. Does direction matter? If the answer is yes, it's a vector. If it's no, it's a scalar. It's a really simple rule, but it is incredibly powerful in physics.
So now we can take this new toolkit of scalars and vectors and use it to describe a journey. And this brings us to two really important concepts: distance and displacement. They sound almost the same, but as you're about to see, they are worlds apart.
So first, let's talk about distance. This is probably what you're most familiar with. It's the total ground you cover, the actual length of your path, every single step, every twist and turn. It's a scalar. It's just a number, like 5 kilometers. You know the odometer in your car that tracks how far you've driven? Yep, that's measuring distance. Now, the counterpart to distance is displacement. See, displacement couldn't care less about that winding path you took. It only cares about one thing: the shortest straight line path from your starting point to your ending point. It's a vector because it has both a magnitude, how far apart the start and end are, and a direction. It's not about the journey, it's all about the final result. Let's just summarize the key differences here. Distance is a scalar, displacement is a vector. Distance depends on the path you take, displacement is totally path independent. This also means the distance you travel will always be a positive number, but your displacement can be positive, negative, or even zero. And this is crucial. Your distance traveled will always be greater than or equal to your displacement. All right, let's put it all together. We've gone over relativity, scalars, vectors, distance, and displacement. So now it's time to test that knowledge with one last example. So here is a classic physics question for you. Imagine you're on a standard 400-meter running track. You run exactly one lap, finishing right back where you started. We know your distance is 400 meters, but what is your displacement? The answer is 0, a big goose egg. Your distance was 400 meters, a scalar value that represents the entire path you ran. But your displacement, that vector measuring the straight line change from your start point to your end point, is 0, because your start and end points are the exact same place. You ended up right where you began. So, let's quickly recap the main takeaways. First, all motion is relative. You have to measure it from a reference point. Second, scalars measure how much, while vectors measure both how much and in which direction. And finally, this distinction gives us the huge difference between distance, which is the total journey, and displacement, which is just the final outcome.
And I'll leave you with one final question to chew on. The Earth travels an incredible, mind-boggling distance in 1 year as it orbits the Sun. But after 1 full year, when it returns to the exact same point in its orbit, what is its total displacement? Ponder that one. Thanks for watching.